This experiment started with me finding this cool method of coating glass in a hydrophobic powder, basically, which I'll show you how to do in a second. But it turned into sort of me seeing if I could get a droplet to spin, which I saw on YouTube. You could get a droplet and make it fall onto this pattern, this kind of carving, and it spreads out, and then when it comes back in, it twirls and spins around. But unfortunately, my slow-mo camera isn't really good enough to actually see what's going on. I tried a bunch of times, but I couldn't quite get it. So I changed modes, and I was thinking it'd be cool to do a sort of resonance experiment. So this is just a speaker and some water. This is sort of showing the standing waves that can appear when you play different frequencies into the speaker. And then I had an idea, which is that you can trap a water droplet by, getting rid of some of the hydrophobic surface and then placing a drop on it. It's sort of tricky to do, but yeah, those are just droplets hanging out. I missed the spot. But once you do get it on that spot, it's really locked in. And then you have a perfect sphere of water. So I was thinking if I could play notes into that, it'll have some cool spherical resonance properties. This is how I set up the hydrophobic surface. I used a tuning fork that I just had lying around, placed a glass slide on it, and then caught the soot from a lighter or a candle. And that thin layer will actually keep water away. The water on top, the only purpose of that is to stop the glass from getting too hot and cracking. But yeah, it creates this nice little layer, and you can draw on it and really just catch a sphere of water. So I was thinking I could play different notes, try to find the resonant frequency of the droplet. But what I found was something really strange, which is this. Once it hits resonance, it spins. I didn't really know what I was expecting. I was expecting maybe a shape change, but it spins like incredibly rapidly. And then this is the other effect that I found, which is you can actually see the curvature of the drop changing, and it's almost lensing the light. You see, there's another example. It's a little easier to see here. I hit a certain resonance, and things get real funky. There's this weird shape going on, a bunch of nodes. You can really see it's standing wave trapped in the sphere. But then I found this, which is kind of disheartening. It means since that water on the other side is also bubbling, it means that it might not be the sphere resonating. Instead, it's just the glass sphere speaker system finding a resonance. So I made this setup to really tell that the sphere of water is resonating rather than just the speaker hits a resonance on its own. So I would shine a laser through this drop, and the drop would refract the light upward. And then once I hit a resonant frequency, the shape of the drop would change, lensing the light like we saw before, and it would change that output beam. And this seems like it might have uses in like in actual labs and things, like a sort of lens that you could control with sound, changing the focal point just by playing different frequencies, tuning it. Yeah, I thought this was pretty cool. But what can you actually do with this? Now that you know the resonance of a drop of water, what can you do? So I found this paper that was quite helpful, and they had this equation for the resonant frequency, omega, on the left. Gamma is the surface tension, M is the mass of the drop, and then L are the nodes. The number of nodes is kind of tricky to see, but I sort of tried to count the bumps on that drop. And from this equation, we can rearrange. The mass is just the density times the volume. We know the density, the radius is around 5 millimeters. We could rearrange to get the surface tension on the surface of that drop. So there's an actual physical thing that we can calculate just from this setup here, finding the frequency of this drop. But yeah, I just thought this was really cool. Wanted to share it.